everybody, let's give this problem a try. So we have a fixed support over here. Alright, so to find the shear force and bending moment functions, first let's figure out that reactions at that fixed support. So I'll just call it point A over here. Okay, so I'll decompose that into x and y components. So since it's a fixed support, it has force and a couple over here. Okay, and now there's this distributed load, which we can represent as a single discrete force, which is the area of the shape. So 1/2 base times height would be 360. And the location of that force is at the centroid of the shape, which is 1/3 of the way over. So that should be 4 feet. Okay, so let's find those reactions. Okay, so in the x direction we got AX, y direction AY minus 360, some torque about, how about over here? So we got, let's see, negative 4 feet times 360 plus the couple over here. All right, so AX is 0, AY is 360, the MA is 4 times 360, whatever that is. 1440. Okay, so we got the reactions at the fixed support. So it looks like AX is 0, so that's nice. Okay, and then there's the, which way is it going? This way. All right, and then there's the distributed load. So let's cut this at some arbitrary point X. We don't want to do it to this representation. Like, you can't just cut it over. Like, that's not right. You have to go back to the original and then cut it at some arbitrary X between 0 and 12 feet. Okay, so if we do that, the left section would look something like this, and like that. Okay, and then the right section would look something like this. Okay, so what was this for? Okay, so given the choice between these two sections, which would you want to analyze? I feel like this one is much simpler, so why don't we do that? Right, so you don't need to analyze both, just pick one, and this one looks much simpler, so let's go with that one. All right, so before I just get rid of it, I just want to note that we cut it at some X, right? So here to here is X. So what is this? The entire beam was 12 meters, right? Here to here. So if we cut it at X, here to here has got to be 12 minus X, right? So this is 12 minus X. How high is this? Okay, let's take a look at the original triangle. The original triangle was, right, this is 60, and this was 12 over here. So what's the slope? Negative. Rise over run like this, right? So that's the slope. And then, right, it's a function of x. And then at x equal to 12, this is 0. So like this. So this is the function. Right at x equal to 0, then it's 60. When x equal to 12, this is 0. So this is the function. So so this is actually right here. It's kind of messy. This. Okay. All right, let me move this maybe when I have more space. Okay, so let's solve for these internal forces and moments. Okay, so in the x direction, again, I have this way like this, right? So in the x direction, minus b. Y direction, what do we do? Okay, let me use the space over here. Now that we have this free body diagram, we can represent this distributed load as a single discrete force, like this. Okay, what's the magnitude? The area of the shape. So what's the area of the shape? 1/2 base times height. There you go. That's the area of this shape. I just wrote it, kind of 1/2 base times height. We can simplify it a little bit, but in fact, why don't we simplify it? So see the minus sign? Okay, and then 12 minus x, 12 minus x squared. And then that leaves us with 60 over 12, and then the 2 over here, so 30 over 12. Let's see. Divide by 3, 10 over 4. Okay. Oh, I should have divided by 6. All right. So let me just write that over here instead of this big mess. Okay, so this is the area of the shape. Now, where is that force acting? At the centroid of the shape, which is 1/3 of the way over this way. So 1/3 of 12 minus x. All right, and then we have all the other internal forces and moments. All right, now let's solve for those. Okay, in the x direction, minus p. In the y direction, v minus this. In some torque about this left end. Okay, so then there's torque from this, so minus 1/3 12 minus x times this. Okay, and then that is in the negative z, so minus. Okay, so here we go. The axial force is 0. The shear is 5/2 12 minus x squared. And then here the bending moment is, let's see, 12 minus x, 12 minus x, so 12 minus x cubed, then 5/2, so then that's negative 5 over 6. Okay, so there we go. Axial force, shear, bending moment. What does it look like? That's just 0 everywhere. The shear will look like, okay, let's see. At x equal to 0, it'll be something positive. And then at x equal to 12, it'll be 0. And then see how it's a parabola? So it's going to look, or a parabola looks like this. So it's going to look kind of like that. All right, so there's shear. This is 12 over here. Okay, and then bending moment. Let's see. So it's so cubic functions look like this, right? And then but then it's minus, so the other way. Okay, so then and then also at x equal to 0, it's something negative. Okay. Oh, actually, I drew this other way, wrong way. There's negative, negative, so like this. Okay. So then at x equal to 12, it's 0. So 0, and then it's going to look something like this, right? So then like that. I mean, not exactly, right? Because cubic would look like this. So there we go. So here's shear, here's bending moment. Oh, and then there was another part to the question, right? Show that the equations for V and M satisfy V equals dm dx. Okay. Where is the... Okay, here we go. So we're trying to prove that this is true. Okay, so if we take the derivative of this with respect to x, what do we get? Okay, so take a derivative with respect to x, minus 5, 6. Okay, so then that'll be times 3, 12 minus x squared. And then see that there's the minus, so times minus 1. So this will become a plus. All right, so then what do we have? We have 5 over 2 times 12 minus x squared. Okay, and let's compare it to, yep. All right, so there you go. I don't know. I mean, this is foreshadowing for the next section of the chapter, which is the calculus relationship between distributed load, shear, and bending moment. Okay, so give this one a try. Let me know if you have any questions, and I'll see you in the next video.